Good day. We will be answering problems from Chapter 24, Capacitance and Dielectrics. We will answer problem numbers 24.47, 24.48, and 24.51. First problem, problem 24.47. In one type of computer keyboard, each key holds a small metal plate that serves as one plate of a parallel plate air-filled capacitor. When the key is depressed, the plate separation decreases and the capacitance increases. Electronic circuitry detects the change in capacitance and thus detects that the key has been pressed. In one particular keyboard, the area of each metal plate is 42 mm square and the separation between the plate is 0.7 mm before the key is depressed. Calculate the capacitance before the key is depressed, and if the circuitry can detect a change in capacitance of 0.25 picofarad, how far must the key be depressed before the circuitry detects its depression? So to solve this problem, we have the following given. The area of the plate is 4.2 times 10 to the negative 5 square meter. The distance between the two plates is 0.7 times 10 to the negative 3 meter. And the change in capacitance is 0.25 picofarad. The capacitance of a parallel plate capacitor in vacuum is given by this formula. C naught is equal to A epsilon naught over D. Substituting the values, so we have the area of the plate, the epsilon naught value, which is this, and the distance between the two plates, giving us the initial capacitance of 5.31 times 10 to the negative 13 farad. Now let us solve for the new value of C if the key is depressed. We may use this. Change in capacitance is equal to the final capacitance minus the initial capacitance. We already have the value for the initial capacitance. So rearranging this to solve for the new value of C, we have this, and substituting the value of our initial capacitance, which is 5.31 times 10 to the negative 13 farad plus 0.25 picofarad, we will have 7.81 times 10 to the negative 13 farad. Using the formula, C is equal to A epsilon naught over D prime. D prime is the distance when the key is depressed. That is the distance between the two plates when the key is depressed. So to solve for the distance between the two plates when the key is depressed, we have this, and substituting the value, this is the area, value of epsilon naught, and the new value of C, giving us 4.76 times 10 to the negative 14 meters of distance. Now, in part B, how far must the key be depressed before the circuitry detects its depression? So the key must be depressed by a distance of change in D, which is equal to D minus D prime. So substituting the value, this is the initial distance minus the final distance, or when the key is depressed. So we will get 0.224 millimeter. So let's have the next problem, problem 24.48, cell membranes. Cell membranes, the walled enclosure around the cell, are typically about 7.5 nanometer thick. They are partially permeable to allow charged material to pass in and out as needed. Equal but opposite charge densities build up on the inside and outside faces of such a membrane, and these charges prevent additional charges from passing through the cell wall. We can model a cell membrane as a parallel plate capacitor, with the membrane itself containing proteins embedded in organic material to give the membrane a dielectric constant of about 10. What is the capacitance per square centimeter of such a cell wall? In its normal resting state, a cell has a potential difference of 85 millivolts across its membrane. What is the electric field inside this membrane? In this problem, we have the following given. the dielectric constant K, which is 10, the distance between the inner and the outer membrane, which is 7.5 nanometer, the potential difference between the two, which is 85 millivolts, and the area is 1 square centimeter. Computing for the capacitance per square centimeter, we will use this formula. To get the C, or the capacitance, we will multiply the dielectric constant with the capacitance in vacuum, giving us K epsilon naught A over T. Substituting the values, we have K, the dielectric constant, epsilon naught, the area, and the distance. This will give us 1.18 times 10 to the negative 6 square meter, or 1.18 microfarad per square centimeter. Now let's solve for the electric field inside the membrane. Since we have the potential difference V and the distance, we can compute for the electric field using this formula. Rearranging this, we have E is equal to V over D. Substituting the values, we have the potential difference, which is 85 millivolts, and the distance between the inner and the outer membrane, giving us 1.13 times 10 to the 7 volts per meter. So this is the electric field inside this membrane. Last problem, problem 24.51. For the capacitor network shown in this figure, the potential difference across A and B is 12 volts. Find the total energy stored in this network and the energy stored in this 4.8 microfarad capacitor. So to solve this, it is important to take note that in series connection, the capacitance is given by this formula, and the voltages add up, the charges are the same. While for the parallel connection, the capacitance is given by this formula, the voltages are the same, and the charges add up. So we will reduce this network. So we will have series parallel reduction. So these two capacitors are in series. Therefore, we will use this formula. Applying this formula, we will get 4.06 microfarad. Next, this one and this one are in parallel. We will use this formula for capacitance, and we will get 7.56 microfarad. Then lastly, this one and these two are in series. Applying this formula again, we will get 2.19 microfarad. This is the capacitance of the whole network. To get the total energy stored in this network and the total energy stored in this capacitor, we will apply these formulas. Solving for the total energy stored, U total is equal to 1 half CEQ V squared. So we have the value for CEQ, which is 2.19 microfarad, and the volt, or the potential difference between A and B, is 12 volts, and we will get 1.58 times 10 to the negative 4 joules, or 158 microjoules of total energy. So this is the total energy stored in the whole network. Now, solving for energy stored in this capacitor, the 4.8 microfarad capacitor, we will use this formula, and rearranging this, we will get Q total is equal to CEQ V. Our equivalent capacitance is 2.19 microfarad, and the potential is 12 volts, giving us 2.63 times 10 to the negative 5 coulomb. Now, we are solving for 4.8 microfarad capacitor's total energy, or the energy stored in this capacitor. So, as we said before, in series connection, the charges are the same. So, this one, and this one are in series. Therefore, the charge of Q 4.8 is the same with the total charge of the whole network. Substituting the values of the charge and the capacitance, we will get 5.48 volts. Since we have the potential difference, we can now solve for the energy. Substituting the value, capacitance is 4.8 microfarad and the voltage in this capacitor is 5.48 volts. Solving this, we will get 7.21 times 10 to the negative 5 joules or 72.1 microjoules. This is the energy stored in the 4.8 microfarad capacitor.